Welcome to lecture 37. In this lecture, I will talk about non-abelian gauge theories. To get started, recall that in lecture 34, we considered the action for a complex scalar field. The Euclidean action was given as a sum of two terms, one term that was given by the gauge covariant derivative of the field phi times its complex conjugate, and a master, for example. We found that this action, in addition to be Lorentz invariant, is also invariant under a local U1 gauge transformation, where the transformation was that the complex field phi went over to the complex field phi times e to the I alpha of x, where alpha could be an arbitrary function, and the gauge field A transforming as A minus the derivative with respect to this function alpha. We also noted from lecture 26, the U1 gauge transformation is isomorphic to a transformation in SO2, and that isomorphicity is explicit if we write the complex field phi into two components, one with a real term or real part phi1 and an imaginary part phi2. In this lecture, I want to get started by investigating how we can generalize this construction from an SO2 gauge group to an SON gauge group. Specifically, I will want to get started by considering an SO3 gauge group. This is easily done by considering the three-component vector model, where phi vector stands for three components phi1, phi2, phi3, that has an action that's given in equation 37.3. Clearly, by construction, the action is invariant under a global SO3 transformations where phi of I, where I now runs from 1 to 3, goes over to the same field phi times the transformation matrix Rij. Clearly, this transformation matrix is nothing else but the rotation matrix in 3 dimensions with respect to two constant angles. We can carry through the whole analysis in SO3, but it's slightly more convenient to use standard notation where we switch to SO2 instead of SO3. What we have to do is rewrite the action for the three-component vector model in terms of the SO2 fields phi. And the steps are basically the same as the ones that we employed when going from the complex scalar field to a two-component vector field. So specifically consider an object capital phi that is given as the sum over individual components phi I times the Pauli matrix C's sigma I. And there's a factor of 1/2 for convention in front. Think of these phi i's here as nothing else but the same three components of the vector field that we wrote the action for in the previous slides. The Pauli matrices fulfill the trace relation that trace sigma I sigma j is twice Kronecker delta ij, and they are Hermitian, so sigma I dagger is equal to sigma I, so that if we take the trace of the sort of term that we have here, the derivative of capital phi times the derivative of capital phi complex or Hermitian conjugate is then equal to 1/4 times the derivative of the individual field components phi I times the trace of sigma ij. And since the trace of sigma of ij is equal to 2 delta ij, this is the same as 1/2 derivative phi I derivative phi I. So the action, which basically is 1/2 derivative phi I derivative phi I, can therefore be written as the trace of this field capital phi times the derivative with respect to its Hermitian conjugate and the mass term. The action 37.7 is invariant under global SU2 symmetry, where the SO2 symmetry acts in the following form. So we have phi going to the exponent of I alpha I sigma I times the field itself. And this is an element of the SO2 algebra. So basically we can plug this transformation into the matrix here. And what we find is that if the alpha here is constant, then we can pull through the corresponding terms here and there, and we find that this is equal to terms that have the following form. So there's a trace of e to the I alpha I sigma I, the two fields capital phi dagger, and e to the minus I alpha I sigma I. And because of the cyclicity of the trace, we can pull through one of these terms so that we get this, the following expression. And since these matrices are elements of SO2, the inverse of the matrix, or the Hermitian conjugate of the matrix, is equal to inverse of the matrix. So this term is nothing else but unity. Because of this, we find that the action here is invariant under global SU2 symmetry transformations that are given in equation 37.8. Now we want to repeat the same steps that led us to the action for electromagnetism. And for this case here, what we have to do is make changes to the action such that it is invariant not only under global, but local SO2 gauge transformations. We can write down the same transformation rule, except that now our alpha i's, which were constants before, are now arbitrary functions of space-time x. Using the same results that we gleaned from the electromagnetism case or the U1 gauge theory case that we had before, we are now tempted to write down an expression for the action that's the trace not only of the normal derivative of phi, but the gauge covariant derivative of phi, where we define the gauge covariant derivative as the normal derivative plus I times a gauge field A, where A is now an SUN gauge field. In order for this expression to be invariant, we can check that this is fulfilled if the gauge field transforms in the following way. And we can make this transformation rule look simpler by introducing new notation. Specifically, if we denote this exponent of I, alpha I of x, sigma I as a matrix U of x, then that SU2 gauge field has to transform as U A U dagger plus I derivative of U dagger in order for the action to be invariant under this local SU2 gauge transformations. One can verify that the covariant derivative of phi transforms as U d phi in that same process. So now that we have written down the equivalent action for the SO2 gauge field, we can ask ourselves what the field strength tensor FAB that we constructed for the U1 gauge theory looks like for the SO2 gauge theory. For the U1 gauge field, we can write FAB simply as minus I, the commutator of the covariant derivatives dA dB. And if we sort of plug in the result from dA dB, because everything is linear, we find that FAB is indeed the result that we had for the U1 gauge field. We can try to do the same thing for the SO2 gauge theory. So if we define the field strength tensor for the SO2 gauge theory as FAB is minus I dA dB, where D is now the gauge covariant derivative for the SO2 gauge field, then plugging in that definition, we find that the result for the SO2 field strength tensor looks similar to the U1 gauge theory, except there is an additional term that comes in as the commutator of the SO2 gauge field. We can ask ourselves whether it actually transforms correctly under gauge transformations. That would mean that FAB has to go as U F U dagger, and we will find that this is the case as part of a homework problem for this particular lecture. Given that this field strength tensor has this transformation rule, it is straightforward to verify that a term such as trace FAB is therefore invariant under local SO2 gauge transformations. We can include such a term in the action, and just customary to include it with a prefactor that's 1 over 2g squared, where this 1 over 2g squared here is just convention. We can call the arbitrary factor g here the coupling constant for the non-abelian field theory. And we can also decompose the field strength tensor into components similar to what we have done for the field capital Phi. So in this case, we can write FAB is 1/2 sum over all 3 Pauli matrices sigma I times FIAB, where FIAB are then the components of the field strength tensor. In this representation, we can write that the trace FAB, plugging in this rule here, and using the trace identity of the Pauli matrices is then equal to 1 over 4g squared FAB, FIAB, where the Einstein summation rule tells us that we have to sum over all Lorentz indices A and B, as well as over the Color underquotes index I that ranges from 1 to 3, which are the 3 Pauli matrices. So if we ignore for a moment the meta part that was given in terms of the field phi, we are left with a classical action for the SO2 gauge theory that is just 1 over 2g squared trace FAB. We derived this result for the SO2 gauge fields that was isomorphic to the SO3 gauge theory group for the 3-component vector model. But it is not hard to generalize this action to an arbitrary gauge group SUN with arbitrary n. In fact, we can just demand that the action for general gauge group SUN is the same as 37.21, which is invariant under these gauge transformations here, where the gauge transformation U is then spanned by SUN matrices e to the I alpha I lambda I, where alpha I is an element of SUN. We can then define generalizations of the Pauli matrices that we then call generators of the gauge group. And in terms of these generators Ti, we can write the field strength tensor, for instance, as a sum over components FIAB times the corresponding generator Ti, where we demand that the generators be arbitrarily normalized such that Ti Tj is just 1/2 delta Ij. In general, the generators for the SON gauge theories are n by n matrices, and they obey the commutation relation commutator Ti Tj is I Fijk Tk, where Fijk are the so-called structure constants of the SON Lie algebra. Note that for n is 2, we have an SU2 gauge theory. In this case, the generators are nothing else but 1/2 times the Pauli matrices sigma I, and the structure constants Fijk are nothing else but the Levi-Civita symbol epsilon ijk, also known as the epsilon tensor in 3 dimensions. Let me note that the FA or the FAB and the FIAB encode the same information. They sort of are just different representations of the same field strength tensor. In particular, we call FAB the fundamental representation of the field strength tensor, and one can think of this object as an n by n matrix. By contrast, the FIABs are nothing else but the adjoint representation, and they correspond to the n squared minus 1 independent entries of this n by n matrix. We can use the properties of the generators Ti to derive the relations between the adjoint and the fundamental representations. So in particular, we can write the components FIAB as twice the trace of the FAB in the fundamental times Ti, the generator. And if we use the commutation rules and the rules for the trace of the generators, we find that this is equal to dA ABI minus dB AIA minus FIJK AJA AKB. Let me summarize that for general N, the SUN gauge theory is referred to as classical Young-Mid theory. And for the special case of N is 3, this gauge theory becomes relevant because it is the right gauge group for the theory of strong interactions, also known as QCD. For the case of N is 2, the SU2 gauge theory that results from this is relevant for the so-called electroweak theory, the unification between the weak interactions and the electromagnetic interactions. This is also known as the Salam-Glashow-Weinberg model. And this concludes the present lecture.